Good afternoon, everyone, and thanks for coming to this astro-seminar. I have the pleasure to introduce Dr. Paul Yeung. He's working at the Institute of Computer Research that belongs to the University of Tokyo, so he's coming from Japan. He's a physicist that is with a strong expertise in gamma ray astrophysics, and more particularly, he's doing research in trying to understand how pulsars, neutron stars, are emitting very high energy radiation. But he's also a member of the CTAO project. I think most of you know what CTAO is. CTAO stands for Cherenkov Telescope Array, and this is an international project that is also very important for our institute, IPARCOS Institute, because we are involved in CTAO, helping to the development of the hardware and software. And as you know, CTAO will have more than 100 telescopes distributed in 2 sites, one in La Palma. And the first telescope of CTAO is already working at La Palma, the large size telescope with a diameter of 23 meters. This telescope is already producing science, especially also in the topic of pulsars, in today's topic. So, the Stephen Yu Pulse, I think in his seminar today, he's going to explain how pulsars are working, especially at very high energy. I think he's also going to explain something about what CTAO is going to do for pulsar. Right? So, thanks for coming.
Thank you, Marcos, for introducing me. So, today I'm going to give you an overview of the pulsar studies at very high energies. So the first fundamental question is, why is the pulsar emission periodic? Well, first of all, we know that the pulsar is rotating very rapidly, and equivalently, in the pulsar field, our line of sight is revolving around the pulsar very fastly. Yes, here I give you a schematic diagram. Yes, this is the trajectory of our line of sight when in a pulsar beam. This is the cross section of a pulsar beam, and our line of sight is rapidly cut through the beam periodically, and this is the reason why we see a periodic signal. So this is the angle between the beam center and our line of sight as a function of the pulse phase. When this angle is minimum, we will see a peak in the pulsar light curve. Well, in principle, a beam's real center is never detectable because no matter how close our line of sight is approaching the beam center, this angle is never zero. There must be some separation between the beam center and our line of sight, so that we are always observing the outskirts of a pulsar beam. We can never see through the real center of a beam. And what is our scientific motivations for pulsar studies? Here I quote a Vela physiograms published by the HEX collaboration in 2023 in their Nature paper. We know that both Vela, Crab, and Geminga and Dragonfly pulsars have a double peak, and a bridge between them. Each pulse signal is asymmetric, and there is also an energy-dependent gamma ray pulse shape, and equivalently, we have a phase-dependent gamma ray spatial shape. This could imply that there are more than one emission site for each pulsar, and noticeably, for Crab pulsar and Vela pulsars, TeV pulse emission had already been detected. And so article notes that there is a diversity of pulse shapes among different gamma ray pulsars. In particular, we see that the bridge shape of the Vela pulsar looks quite different from those of the Crab and Geminga pulsars. So here, there is clearly a bump in the Vela bridge, but for the Geminga and Crab pulsars, their bridge phase looks more like a valley floor. They are flat. They look flat or just slightly inclined, but we don't see such an exaggerated bump as we saw in the Vela light curve. So there is an open question. Yes, although we see such a difference among them, could they be still within the same general picture? Well, it is because although they look like a valley floor, but if we fit some arbitrary model with triple or quadruple components, we can still obtain good fits for Crab and Geminga pulsars. And so we have another open question here. If the bridge is actually a peak 3, then where is the peak 4? Well, if we think in terms of the north-south symmetry, and as long as we see P3, then we would expect P4 to exist as well. So yes, but the point is such a hypothetical fourth peak is not intuitively seen on our basogram. So there could be, due to a number of reasons, in scenario A, maybe the P4 is simply unfavored by our lab site, and this could be the simplest reason why we do not detect P4 for Vela, Crab, or Geminga. And there's also another possibility that the P4 is just seriously mixed up with the other peaks, so that this P4 is not distinguishable from the other peaks. And the scenario C is that maybe the pulsar geometry is intrinsically asymmetric. Yeah, if it is asymmetric, then it is very natural that the P4 doesn't need to exist. And the last possible scenario is that the P1, P2, and P3 for the bridge are actually different parts of the same beam. In that case, P4 doesn't need to exist as well. It is very important to judge the relative visibility of these four scenarios from some advanced theoretical modeling. So I would like to introduce some candidate shapes of a pulse signal. So we usually characterize a pulse signal in 3 different aspects. We will talk about the pulse width, for example, how wide the full path maximum is, and we will also talk about the sharpness, how sharp it is, and also the asymmetry between leading ring and trailing ring. The left rings and right rings do not need to be symmetric. Yet we usually see some that they are generally asymmetric. So in terms of the sharpness of peak, we know that a Laplacian model is sharper than the Lorentzian shape, which is also sharper than the Gaussian shape. Uniquely, the Laplacian peak is not flat, mathematically speaking. It is continuous but not differentiable. Yeah, it is. You see that the Laplacian peak is not flat, unlike the other 2 candidates. So, in terms of the tail, we know that the Lorentzian tail is much more obvious than the Laplacian and Gaussian tail. So the Laplacian distribution is promoted by this paper based on the wavelet packet coefficient distribution, and theoretically speaking, this Laplace distribution could be linked to the so-called caustic effect. Yes, here I quote an image of the caustic effect in water. Yeah, this could be analogous to pulsar, the pulsar case here. So, and here I would like to introduce how the effect of time delay influence the pulse profile. Yes, the idea is that an emission size of a pulsar is at a certain separation from the pulsar center. So it takes some time from the pulsar emission site photon to reach. Yeah, it takes time for the photons to reach us from the emission site, and the times taken for north and south beams to reach us are different in principle, so that we will see the angle between beam center and line of sight as a function of pulse phase is looking like in this way, and this effect could account for why the T2 to T1 phase intervals are less than 0.5, and this could also account for why the leading ring and trailing ring are asymmetric. This effect can account for these two features at least partially. There could be some other factors. Well, and here it is assuming the north-south configuration.
This can be checked with the radio pulse, right? So you have the gamma pulse and the radio pulse. If it's a geometric effect, one should see it in both, right?
Well, actually, yes. Well, for example, at least for FRAP, we know that these two features are observed from radio to gamma ray flow.
Beautiful, luminous stuff.
At least for the FRAP pulsar, yeah. We see these two features regardless of the energy band from radio to gamma ray. So there are a number of proposed gamma ray emission regions of a pulsar, including the polar cap, slot gap, outer gap, and base of the ring models. And more recently, we also have a model of wind current sheets. This model suggests that the emission size is from a current sheet propagating beyond the light cylinder. Yeah, you see that here all these emission sizes are within the light cylinder or at the edge of the light cylinder, but this emission size could be propagating beyond the light cylinder, and this is the wind current sheet model. And in terms of the mechanisms, people suggest that there could be a simple curvature radiation consisting of the curvature radiation from primary particles as well as synchrotron radiation from secondary pairs. And people also propose that inverse content scattering, that a low energy photon is upscattered by the relativistic electrons accelerated from the pulsar, and then the higher energy photons would emerge out. And now, so I would like to say that our rapidly developing CTAO is very useful for our further understanding of gamma ray pulsars. So the CTAO is a new generation of ICTs. It is an array of many ICTs. It has unprecedentedly good sensitivity from 20 GeV to 10 TeV. The energy band is complementary with Fermi-LAT and other ICTs, especially our large size telescope prototype LST1 has a threshold of about 20 GeV. Its sensitive energy range is greatly overlapping with Fermi-LAT and magic energies. And so the results observed with this telescope is very suitable for cross-checking the Fermi-LAT and magic results. This is the sensitivity curve. And now I'd like to point out the differences between pulsar analysis and non-periodic source analysis. For non-periodic source analysis, we define the source and background counts or the on and off counts based on the spatial regions. But for pulsar analysis, we define on and off based on the pulse intervals instead of spatial regions. The idea is that the on count is varying with the pulse phase, but the off count is constant with time, so that we can compute the pulse counts of a pulsar as the on counts minus the weighted off counts. So, but I would like to note that data get on the spatial region is still quite important for optimizing the signal to noise ratio. Now, you would like to ask, the pulsar is also a source, so why we don't apply the spatial region cuts for pulsar analysis? The reason is that pulsar is usually spatially coincident with other objects. For example, the pulsar could be surrounded by a pulsar nebula, which is also embedded within a supernova remnant, and beyond the supernova remnant, we could even have a TeV halo. So if we apply the non-periodic source analysis techniques for pulsar, we cannot distinguish the pulsar emission from these coincident sources. But pulsar analysis could, yeah. So when we define the off and on counts based on the time domain instead of the spatial domain, we will automatically distinguish the pulsar emission from all these coincident objects. And so this is the outflow of studying a pulsar with IACT gamma ray data. First of all, we prepare the files of photon list and the timing ephemeris, and we will assign the places to photon list. Yes, so the timing ephemeris is a timing solution for a pulsar during a specific time of observations. This is the format of the timing ephemeris, and yes, this is an example for Vela pulsars. I would like to note that the duration of the ephemeris validity should fully cover the observation period of the data that we intend to analyze. Otherwise, it doesn't work. It is because the pulsars could frequently have timing noise and even some glitches. Yes, glitch means the frequency derivative suddenly change dramatically and slowly recover to a generation. There could also be some permanent unrecoverable change in this distribution, and that's why we should make sure that the validity of the timing ephemeris cover the full observation period of the data. So this is an example code of assigning the pulse phases to the gamma ray photon files. We use the Python package called PINT. We apply it to the already reduced photon lists, and this is to generate a phase list from the photon files. And so this is an example of the phase-folded light curve, and we usually call it the phasogram. So the phasogram is the idea to divide the full phase into a number of phase bins. For each phase bin, we stack all kinds that are within that phase interval. The statistical error of the count is just the square root of the count according to the Poissonian statistics. So yeah, it is very interesting to look whether the pulse shape changes from energy to energy. And then, yes, this is the code for plotting the phasogram. Now I would like to introduce some statistical concepts. So after we define the on and off phase intervals, we use this Lemma formula to compute the free trial significance of the excess. So here, we substitute the phase interval, which is defined as the peak phase and also the off phase as the phase of uniform count. So this pre-trial significance has not yet taken into account the elsewhere effect, but there could be a bias due to the definitions of on and off phase intervals. And after obtaining a phasogram, we would also like to investigate the spectrum, the phase resolved spectrum, which is the spectral energy distribution during just a specific phase interval. So this is an example for the proposal observed with RST1. It is interesting to note whether the spectral index is dependent on the pulse phase or not. And so this is how we compute and plot the phase resolved spectrum. We use the gamma pi package. The technique is quite similar to the spectral analysis for non-periodic sources, and the only difference is that for pulsar analysis, we define the on and off based on the phase intervals instead of spatial regions. And so that's the end of my talk. Thank you so much.
So how many photons is the graph you just showed to transparency before the end? You were showing the energy square the MDE.
You mean
the spectrum?
The spectrum.
Yes.
Yeah.
How many photons is that?
The photon number.
Count.
The photon count for all these is for the whole spectrum. It is roughly around. Yeah, it is. Yeah, it is. Yeah. yeah, a sum of these four things.
So in this same slide, what are you fitting to the data? What are those kind of things?
They are actually just fitting a toy model consisting of two Gaussian.
Okay, so you're
Actually, they actually neglect the bridge. Yeah, they neglect the bridge component. Yeah, they just fit a double Gaussian to characterize each phasal graph. Yeah, they don't care about the bridge. Yeah, but of course for RST1 data, the bridge is not too significant. So that even neglecting this bridge division, the fitting is still satisfactory. But of course, ideally, this bridge needs to be characterized as well. But here they just fit the P1 and P2.
Coming back to the beginning of the presentation, I haven't understood why it was spec 4 peaks.
Okay. Well, so it is just this is just based on the north-south symmetry. So that because here we make an assumption that the P1 and P2 are two emission regions in the north hemisphere and south hemisphere respectively, and then in that case, this P3 is also located either in the north or in the south. In that case, then we would expect the P4 should be somewhere here as well.
Can you correlate that with the radio pulse?
Radio?
With the radio, yes.
Well,
if it's a geometric effect, it has to appear in both.
The one is in radio, you have many peaks. In the light curve in radio, have much output that in gamma.
Well, but at least for Fred Pulsar, the radio profile is not very much different from the gamma ray, at least for Fred, yeah.
In the other pulsars, radio that are quite complicated to understand. Have many peaks.
Yes. And our idea is that each peak could correspond to a different emission region or mechanism.
Could you have a quadrupole field instead of a dipole field?
Like a
quadrupole field.
four points.
Quadrupole. I mean, a different magnetic field structure instead of a dipole, a quadrupole. This is what you were asking about. Time principle. Also, you have presented a calculation, I think, go on. Go on. This.
Yeah.
Can you include the relativistic aberration effect?
Yeah. Here, you are asking how I obtain this rule?
Yes.
Okay. Well, this is let me draw something on it. So, in the pulsar geometry, so let's say this is the pulsar center, and now let's say the emission site. Yeah, this is the pulsar center. Let's say the emission, and this is the rotational axis, and we don't know how. Okay, let's forget about the magnetic pole. Let's say the emission site is here. Let's say this is the emission site, and let's say that this is the beam one, and okay, and there. Let's say this is the separation D, between the emission point and the pulsar. Of course, the emission site is not a point. Of course, it is the actual emission site should be an unknown extended 3D structure. But let's say let's approximate it as a point, and this is D is the separation between the emission site and the pulsar center, and there is an angle, and this emission site is at a certain angle from the rotational axis, and maybe our line of sight, let's say our line of sight is here. This is our line of sight, and there is also an angle between the line of sight and the rotational. Let's call this theta A is the angle between line of sight and the rotational axis, and here the angle between rotational axis and the emission point, let's call it theta phi. So if we assume some certain values for theta A, theta phi, and also certain values for B, then we will obtain this kind of, we can easily compute this kind of curve. Yeah, so, yeah, well, if we assign different combinations of values to these three parameters, of course we will obtain a diversity of the distributions. Yeah, so this is based on a certain combination of these three values. Yeah.
I'm not an expert on this. What is the typical size of the outflow of the pulsar?
The typical size of the outflow. You mean the outflow?
The extension, when you
the
mention
jet,
the method on source, off source, I mean, maybe I missed it. How do you define the off position?
Well, as I said, here for pulsar analysis, we define the on and off based on the time domain instead of spatial domain. So the idea is, for example, let me show you an example light curve. Yes, so this is the example light curve. The idea is we define it. For example, this is the on, this is on, and this is off. Yes, the idea is that this component is constant with time, but this is pulsating with time. So that in that case, in principle, we can care less about the spatial regions. But of course, in any case, we don't want too much noise to exist, so that we still need to make a spatial region cut. But this cut could be looser, or relatively looser for pulsar analysis.
Any question online? Any other questions here? If not, we can thank the speaker again.
Thank you.